Our understanding of matter and atoms has evolved quite a bit over the past century, and it continues to evolve. We'll pick up the story at the beginning of the 20th century, when Rutherford had performed experiments that indicated that most of the matter of an atom was concentrated at its center, and this led to the planetary model of an atom that looks something like this, where the heavy positive protons are at the center and the light negative electrons orbit around it like planets around the sun. Around 1913, Niels Bohr expanded on that model to explain the emission spectrum that is observed when elements are heated. Let me take a few minutes to explain what is meant by an emission spectrum. When an element is heated up, it emits light, but only specific colors or wavelengths, not the entire spectrum. This set of discrete wavelengths that the element emits is referred to as its emission spectrum. Here is a chart showing the emission spectrum for a few of the elements. You can see in this example that hydrogen emits 4 wavelengths of light in the visible spectrum, 2 shades of violet, 1 shade of blue, and a shade of red. There are also wavelengths emitted by these elements above and below the visible spectrum. The emission spectrum for each element is unique. You can see in this chart how different the emission spectra are for these 6 elements. An emission spectrum is like a fingerprint, and it's a very useful tool when identifying substances in a lab or in astronomy. The term spectroscopy refers to this method of identifying substances by their spectra. To explain why we see only discrete wavelengths like this, as opposed to the full spectrum, Niels Bohr proposed this. Electrons for each element can only exist in discrete energy levels, meaning only in specific allowed energy levels. With this in mind, Bohr modified the planetary model of the atom, stating that these energy levels are discrete and that the electron can move between these energy levels but cannot exist between them. By the way, it's fine for our purpose to view the electrons in nice circular orbits like this, but since the electrons have a wave-like nature, the space that it occupies is actually more cloud-like. But again, this picture suits our purpose. So let's consider what happens when an element is heated. Here's an atom with an electron in the E1 or first energy state. When the element is heated, the electron gains energy and jumps up to a higher state, let's say E3, the third energy state. The electron will not remain at the higher energy state, though. It will ultimately drop back down. So in this example, it may drop back to E2 or it may drop back to E1. If it drops back to E2, then the energy that the electron loses is emitted as electromagnetic energy or light energy, where the amount of energy emitted is equal to the difference in the energy levels between E3 and E2. Or it may drop from E3 all the way down to E1, in which case the amount of energy emitted would be equal to the difference in the energy levels E3 and E1. So in general, the energy of the photon emitted is equal to the difference in the atomic energy levels. As we know, the atomic energy is HF, so substituting this in, the equation becomes this, where we can see that the frequency of the emitted light is determined by the difference in the energy levels as the electron transitions down from a higher level to a lower level. In this equation, be sure to use SI units, so the frequency is in hertz and the energy is in joules. As an example, let's say that an electron in a hydrogen atom transitions from the third energy level to the second energy level, where the difference between the energy levels is 1.89 eV, and we want to find the frequency of the emitted light. We need to convert this energy to joules first. 1.6 times 10 to the minus 19 joules equals 1 eV, so multiply by that ratio, and we get the difference in the energy levels is 3.02 times 10 to the minus 19 joules. Now we can use the equation derived a moment ago and solve it for frequency. And then, plugging in the values, we get that the frequency of the emitted light is 4.6 times 10 to the 14 hertz, or 460 terahertz. This frequency is in the red part of the visible spectrum. So now if you recall the chart we looked at before, that would account for this emission line here. The reason why each element has a different emission spectrum is because the discrete energy levels for each element are different. And that means that the differences in the energy levels are also different. And that in turn makes the frequencies of the emitted light different. When analyzing the energy levels and the resulting emission spectrum, it's common to represent the energy levels in a plot like this, where the y-axis is energy and there isn't an x-axis. It's just spread out horizontally like this for convenience. You'll see why in a moment. The lowest atomic energy level, or the first energy level, is E1, which is also called the ground state. The first energy level above the ground state is called the first excited state. The term excited in this context means that the electron or the atom has additional energy beyond the ground state energy. The next energy level is called the second excited state, and so on. I've just shown 4 energy states here, but they actually go up indefinitely. Notice that the numeric subscripts for the energies, E1, E2, etc., don't agree with the terminology of first excited state, second excited state, third excited state, etc. So be careful with this. Let me demonstrate how we might use this chart. Say we know the values of the discrete energy states for a substance, and the substance is excited to the third excited state, which is also called the fourth energy state. We can determine the frequencies of the emission spectra by recognizing that the energy may drop from the fourth energy state down to any of the lower states like this. And if the substance is excited to the fourth energy state, then all of the lower states will be occupied as well. So considering the third energy state, transitions from E3 to E2 and to E1 will also occur. And then considering E2, there is also a transition down to E1. Basically, we've identified all of the possible energy transitions from the highest energy state on down. In this particular case, there are 6 transitions, and so there will be 6 emission lines, though, by the way, they may not all be in the visible range. We could go on to find the frequency of each emission, as we did in the prior example, by using the equation HF equals the difference in the 2 energy levels involved, solve it for the frequency, and applying it to each of the 6 energy transitions. And then we would get the 6 frequencies. So you might wonder, how do we determine these energy levels? The energy levels for each atom are based primarily on the Coulomb forces between the electrons and the protons, but are also affected by some quantum effects that we won't get into. Neutral hydrogen is the easiest element by far to analyze, as it only has 1 proton and 1 electron. Bohr was able to derive an equation for the energy levels of the hydrogen atom with classical physics principles and the concept of quantization. The derivation is in the textbook, and here's the resultant equation for the energy levels. The energy of the nth level is equal to the negative of 13.6 eV divided by n squared, where n is the number of the energy state, also referred to as the quantum number. So in the previous discussion, if we wanted to determine the energy level of the fourth energy state, then n would be 4, and so plugging into the equation, we would have negative 13.6 eV divided by 4 squared. Notice 2 more things about this equation. The constant 13.6 is in eV, so you may need to convert it to joules, and the fact that there's a negative in the equation means that the energy levels are always negative. And you might wonder why this is. Here's an analogy. If we consider the energy of this diver, we could define the gravitational potential energy at the diver's highest location to be 0, and then the gravitational potential energy of the diver anywhere below that height would need to be negative. We've done a similar thing with the energy of the atom. The highest energy is n equals infinity, and plugging n equals infinity into the energy equation, the energy comes out to be 0 at the highest level. So all of the energies below it must be negative. Let's use Bohr's equation and calculate the energy levels for the first 5 energy states for hydrogen. So here they all are, and now let's put these on an energy plot so you can see that the energy levels are not evenly spaced, and the transitions get smaller and smaller as the energy levels increase. Let's look at all the permutations of the energy transitions. Notice how the transitions are organized. All of the transitions to the ground state are called the Lyman series. All of the transitions down to the second energy state are called the Balmer series. All of the transitions down to the third energy state are the Paschen series, and so on. Each set is named for the person who was significant in their discovery. Note that the highest transition shown in each series in this plot is from the 7th energy state, but transitions from all higher states are also part of each series, so each series is actually an infinite number of transitions. The Lyman series, for example, would also include E8 down to E1, E9 down to E1, E10 down to E1, all the way to E infinity to E1. The Balmer series is perhaps the most well-known series. It was the first one discovered because 4 of the wavelengths are in the visible part of the spectrum. The other transitions in the Balmer series, as you can see, have greater energies, And if you calculate their wavelengths, you would find that they are in the UV range. For the Lyman series here, all of the transitions have a greater energy than the 4 visible Balmer series transitions, so they are all in the UV range. The other 2 series shown have smaller energy transitions, and they're all in the infrared range. In addition to deriving an equation for all of the energy levels in the hydrogen atom, Bohr also derived an equation for the radius of each energy level. Bohr is still picturing the electrons in circular orbits. While we know that is not exactly correct, it's still a good approximation for the size of an atom based on its energy state. Here's the equation that Bohr derived, where again, n is the number of the energy state, or the quantum number, and A0 is a constant 0.0529 nanometers, also known as the Bohr radius. One last thing, you may wonder why there are discrete energy levels in atoms. Bohr assumed that there are, and this assumption is justified by the fact that it explains spectral emissions that we observe in the elements. But interestingly, it's also substantiated by de Broglie's theory of matter waves. It turns out the orbital path that can be calculated from Bohr's radius equation is consistent with the de Broglie wavelength of an electron. So to show you what I mean, if this is a hydrogen atom with the first 3 energy levels shown, the orbital path of the first energy level happens to be the same length as the de Broglie wavelength of an electron, and the orbital path of the second energy level is the same length as 2 de Broglie wavelengths, and the orbital path of the third energy level is the same length as 3 de Broglie wavelengths, and so on. So there's a strong connection between the de Broglie wavelength of an electron and the discrete energy levels in a hydrogen atom. And so this is more evidence for the existence of matter waves. Well, that brings us to the end of this topic. I hope you've enjoyed it.